Hello everyone, welcome back to another machine learning video. So this time I'll be showing off a basic example of how to use a neural network to read numbers. Alright, so I actually did this project for my coding club, and this is kind of the final project that I kind of devised for the students to do, and this kind of gives some explanations along the way, but most of the stuff is in person. But I think I've covered it well here. So let's begin. First, we have to import some libraries or modules. So Keras, machine learning, of course, and then NumPy, that's for managing our data, but it also can do math and the linear algebra. Alright, and then matplotlib.pyplot, that is for the plotting and the visuals. And then we import MNIST, the name of a dataset with all the written numbers. That's our data. So we load it into xtrain, ytrain, xtest, ytest using the function loadData or the method. And essentially, this just kind of downloads the data into these variables. So xtrain, so anything with x is basically just kind of used for the machine learning algorithm to assess and then use that to predict y. So in this case, x would be an image or many images of written numbers, and then y would be the corresponding actual correct answers. So like, for example, if you drew a 1, then that would correspond to the number 1. Alright. Next is we can just print the shape. So that's very simple. We just kind of get a general idea of how many data points there are. Alright. And then for data preprocessing, we have to encode our y values, so our labels or classes or categories. We have to turn them, because right now the shape, you can tell, it's just one column, that is 60,000 rows. And we have to turn that into still 60,000 rows, but also 10 columns, one for each of the numbers. So each digit, basically, if it is the actual correct number, then we set it to 1 for that column in the row, and then the rest of the row will just be zeros. And this function achieves that. Now we run the function on the training and the testing data, and again, I didn't explain this at the beginning, but the training data is kind of like the review material, like a review sheet that a teacher might hand out. But then the test is actually how you know the student learned from the review. Alright. And then, so for training, the y value for the training, that's kind of like the correct answers to the homework or the review material. And then xtrain would kind of be like the problems on the homework. And then xtest, ytest, those are kind of the same idea, but just for the test. And we don't actually let the algorithm see the correct answers for the test, of course, but we do let it see the correct answers for the training data. Alright, now we create our model. So this is something I went over during the club in person. It's kind of too difficult to explain it right now, but basically just know that the convolutional layer, it's kind of like applying some filters to detect patterns in the images, and then pooling, that makes the image size smaller while capturing the major details in all the patterns. And then we repeat this process, kind of extracting the patterns, making the pattern smaller or making them kind of condensed. And then we do that 3 times. You can do this any number of times. There's really no set rule, but this is just an example, and these numbers I kind of just came up with them. And, it's like kind of just random testing. And then at the end we flatten it. So at the end we have kind of a very small array actually. So there's not really, the images are getting really small, so we can kind of just flatten them into a single array and then use our neural network on it. Oops. Yeah, so the first layer is kind of like actually doing, I mean, I guess both are, but so the first layer is kind of taking in those several outputs in the array and then doing some multiplication, and then that passes it to the final layer, which will output the probabilities of each digit. And we can summarize our network structure, and we see that there are 1,600,000 and a little bit more parameters. So that's quite a bit. But it's actually not a lot compared to the biggest models that exist today. For example, some of them, like BERT by Google, it has several billion, which is kind of crazy. So this is kind of just like a toy convolutional neural network, but it does the job it kind of was created for. Alright, so now we can compile, and these details are kind of not too important, but for the optimizer, you pick Atom. Atom is kind of just something that decreases the learning rate as the model gets better, and that's kind of what most optimizers do. The learning rate, that's kind of difficult to get into, but it's kind of like the speed at which the model will jump to conclusions. For example, if a model saw that 2 plus 2 is 4, 2 times 2 is 4, and 2 to the power of 2 is 4, then it might, if it had a high learning rate, it might jump to the conclusion that 2 minus 2 is also 4, but or 2 divided by 2 is also 4. But if it had a low learning rate, it wouldn't really jump to those conclusions. It might ask a little bit more, try to see what's really going on. That's kind of an analogy. It's not exactly how it works, but as it gets better and better, if you jump to a conclusion, you might actually become worse at the problem solving than before. So that's kind of why you need an optimizer. And for the loss, this is kind of just seeing how much the guess was off. So for example, if you guess like 1, but the actual answer is 2, then the loss would be quite large because you didn't guess the right answer. But if you were to guess, let's say 1 with a kind of low confidence, so like, for example, you guess it's probably 50% 1, 50% 2, and the other ones are just 0. But the correct answer is, let's say it's 1. In that case, you might get a slightly lower loss because you kind of got the general idea. There's a big chance that it might be the number 1, but you also kind of weren't too confident in that, so that kind of lowers the score. But if you guess it's definitely 1 and then the correct answer is 1, the loss will be very low. So the goal is to minimize that loss. Whoops. Control Z. Just delete that. Alright. So then for metrics, this is kind of easy to understand. It's kind of just accuracy. Like, it's kind of like the same thing as 3 free throws. So, like if you throw, 10 free throws, and then you hit like 6 of them, then you have 60% accuracy. And if you hit 7, 70%. It's kind of the same thing where if you guess the correct number, the accuracy goes up to 1. Minimum is 0, of course. And then we train the model using this very dandy function, model.fit. So I just trained it for 4 epochs or epochs, doesn't really matter. But the more you do it, the more the model might overfit. That's a specific term to the training data. That means it's kind of like if you only know how to do the homework problems, and then if the teacher changes the numbers a bit on the test, you won't actually know how to do the problems. But that's kind of a discussion for another day. I don't really want to go too in depth, but that's a basic idea. That's why I did like a low number. And basically it looks through every single image a total of 4 times. And we have validation data. So the validation data is kind of like the test, right? So we're kind of judging it more based on how is it doing in terms of the test rather than how is it doing in terms of the homework. And so you can see the training happens here. And it kind of gets a little bit worse after the 4th epoch. But it's still pretty good. Alright. So now we can plot. So this is how we assess the model. So I've kind of made the window very close to 100% accuracy because for this type of problem it actually improves really quickly. So the blue line is the training accuracy. You can see it goes up more than the validation accuracy. Validation accuracy, you can see it kind of stays level, and if you train long enough, then you'll kind of see the validation accuracy. It might actually go down because you're overfitting to the training data. And you can already see that the accuracy for the training set is actually going above already. So that's a sign of overfitting. So it's good that I stopped it at 4 generations. Now, another issue is, well, it might kind of look weird that the validation accuracy starts off at 98% when the training accuracy is 95%. It's like, if you got 95 on the homework, how could you get 98 on the test? Well, this is actually because when we check for validation accuracy, it's kind of after you've done all the homework, but when you're doing the homework, you're actually improving at the subject. So it's kind of like if you have that accumulated accuracy, it'll be a bit lower because you weren't as smart the whole time. When you're doing the validation, you actually have all the knowledge from all of the training. And now we can look at the loss. So the loss starts off quite high actually for the training, but you can see it goes down, and at the end it goes actually below the validation loss, and the validation loss actually starts to increase a bit. So this is the error. So basically higher is bad and lower is good. So this is kind of the same phenomenon as you see above. It's overfitting. Alright, so we got an idea of how the training history occurred. Now we can try to plot some of the guesses and then see if they make sense, or maybe like the model's not doing as well for certain numbers, or if it's like it's only getting wrong the ones that are really weird. So here I just plotted one example. So P is prediction. It predicts a 7. T is the true answer, 7. So very nice. I would expect it to get that. Here I plot 100 of these. And these are all incorrect answers, by the way. So I do that with this special loop. You guys can look at that later. So let's look at some of these. Let's see which ones are the most kind of understandable errors from the algorithm. So it's kind of like the ones where you kind of expect like, oh yeah, that definitely makes sense. Alright, so the first one, this one's kind of weird, like, oh, I kind of see the 5 now, so I can kind of understand how I got that one wrong, because they didn't complete the loop for the 9. Now, here, yeah, that looks like a 7, there's like a little bit there, so I think the most advanced models will be able to catch that because they're kind of trained in more detail with more parameters. So these mistakes are less common if the model gets really smart. This one, so I guessed 8. Yeah, I mean, it kind of looks like it could be an 8 if you drew another loop there, but it doesn't really seem like it that much. Or it might be the disconnect there with the curve on the left. But I could kind of look at this all day, but this video can't go that long, so you guys can just pause the video, look for some interesting ones. Let me look for my favorite one. This one is really weird. Like, how do you just stop drawing the loop there? Like, you didn't even, this person didn't even stop it like, maybe like up there. They just stopped it kind of, it looks like a yam or like a carrot, something like that. But yeah, that's it for this video. Thank you guys for watching, and see you guys next time.